Welcome back everyone. So today I have brought another interesting problem from mechanics, and if I have to categorize it specifically, I would say it's an NLM question. So let's give it a try. First, I'm reading out the problem once. A heavy flexible inelastic chain of length L is placed almost symmetrically onto a light pulley which can rotate about a fixed axle as shown in the figure. What will the speed of the chain be when it leaves the pulley, right? So first of all, let me tell you a wrong method, a wrong approach which many of you are thinking after reading out the question. Okay, is that this one is so easy. So actually what you can do, but that's a wrong approach, is if you think that the rope will detach at this position. I mean, when this length will be L and this side length will be 0, I mean the whole length of the rope gets slipped over the pulley and it finally gets detached from the pulley, and from this situation to this situation you can conserve the energy and you can find out the velocity with which the chain will detach from the pulley. But that's actually not correct, because we are not sure that if the rope gets detached only after all of the L by 2 part from the left gets pulled over to the right, or there is some portion still left in the left half when the chain gets detached. So we have to find out that at what position and at what time the chain gets detached. We can't just see the figure and tell this abruptly. We have to mathematically calculate that, right? So just for a precursor, I would I would do another derivation where I will show you that the internal tension in a rope when the rope is moving with the speed v would be some lambda v square, where lambda will be the mass per unit length. Sorry, I forgot to mention the shorts. Actually, it's from 200 puzzling problems. So it's question number 105, right? And in 104 you will get the derivation of internal tension equal to lambda v square. Anyway, I am showing that here, so you need not to worry that. So let me prove that one first. Let's say this is kind of a rope, whatever be the shape, and the rope is moving with a constant velocity v, right? So as it is inelastic, all the points will be moving with speed v only. So let me just take a small element, let's say this one, and its radius of curvature is, let's say, r. It is subtending an angle d theta, let's say. So internal tensions I'm showing like this, T and T. So this is the bisector angle bisector, so this angle will be d theta by 2, and this one will also be d theta by 2, alternate angle, as this one and this one is both vertical lines are parallel. So this whole angle was 90 degrees, so this angle will be 90 degree minus d theta by 2, so this angle must be d theta by 2. Similarly, you will get this angle as d theta by 2. So this component of tension and tension gets cancelled, but this component will be t sine d theta upon 2, and this will be also t sine, sorry it looks a bit clumsy, let me erase r from here, and this as t sine d theta by 2. And as it was moving with a speed v, so it will have a centrifugal acceleration. If we sit on that frame, I mean the non-inertial frame, we will sit and balance the forces. So we'll write a centrifugal force outward. Let's say the mass of this element is dm, it will be dm times v square upon r. So if we balance the force, we'll get 2t sine d theta upon 2 as dm v square upon r. Now what will be dm? dm will be lambda times r d theta. I have assumed lambda as mass per unit length here, right? And r d theta is obviously the length of that element, rope element. So I'm substituting it here, lambda r d theta v square upon r. R gets cancelled. And now as d theta is very small angle, you can write sine d theta by 2 as d theta by 2. That's our approximation for small angles. So you can write 2t into d theta by 2 equals to lambda v squared d theta. D theta gets cancelled, 2 gets cancelled, and t comes out as lambda v squared. And interestingly, it is independent of the radius of curvature. I mean, let's say for this rope, whatever be the point, whatever be the radius of curvature, at each point the internal tension T will be lambda v square only. It is dependent on mass per unit length and velocity of the rope. So that was a precursor derivation, I would say, for this question. So this internal tension developed when there is no contact with any other body, right? So when the rope will get detached, we will claim that tension in the rope will be this much only, lambda v square. So let me draw the diagram once. Let's say this is the pulley, and at this instant, okay, draw a bit. Yeah. So let's say this was the initial level. I mean, this was L by 2 and this length was also L by 2 initially. And finally, this left part has moved up with a distance of x, and the right hand part has moved down a distance x. And at this instant, we are assuming that the rope gets detached from the pulley. Okay. So we will separately write the equation of motion for right hand side and left hand side. So for right hand side, let's say if this is my system, what will be the forces? There will be gravity force downward acting. What will be the value of the gravity? I mean the weight of this part will be lambda, mass per unit length, into L by 2 plus x. This is the mass times acceleration due to gravity. And here will be a tension, internal tension, and that value is lambda times v square. We are supposed to find v only, that at what velocity, or rather you can say like this, when the rope is getting detached, what is the velocity of the rope. And if this is my system, then I would say the weight is lambda times L by 2 minus x into g. This is the weight of this part, and this is the internal tension, that is lambda v square. Sorry. So if we write the equation for both parts, for right hand part, let's say right, we write this minus this as mass times acceleration. So we'll write this is the mass and this is the, let's say, acceleration, because if we are assuming that right hand part is coming down with acceleration a, so left hand part must be going up with an acceleration a. That much you can say for sure. And similarly, I'm writing the equation of motion for left part. For left part, we can write lambda v square minus lambda times L by 2 minus x into g. So lambda times L by 2 minus x into a. This. Now we'll try to eliminate a, because a is not required, right? And we have assumed that. So let's get rid of a. What we can do, we can mark this equation as 1 and this one as 2. Then we will do 1 divided by 2. In that case, we will get L by 2 plus x into g minus of v square on v square minus L by 2 minus x into g equals to L by 2 plus x on L by 2 minus x. Now you just cross multiply this with this and this one with this. So we will get L square by 4 minus x square times g minus v square times L by 2 minus x, v square times L by 2 plus x minus L square by 4 x square times g. So let's take v square terms at one side, we'll get v square L, and g terms other side, then we will get L square by 2 minus 2x square times g, right? So Yeah, let's keep it here. Now we'll use another equation. So this is one of our main equation, and next we'll take help of energy conservation, writing as energy conservation. So initially, I mean, the change in potential, you can equate the change in potential energy is equals to change in, I mean, the decrease in potential energy is equals to increment in kinetic energy, right? Because mechanical energy is conserved. So all the parts of the rope is fixed, I would say, except, let's say, this part, sorry, this one, we're assuming, because this part was previously there, this L by 2 length, and there was a L by 2 length here. Now we can assume that, let's say, this part of length have been substituted here. So we'll just calculate the change in potential energy of this x length part, right? So we would say that initially the center of mass of this part was here, and now the center of mass of this part is here. This was x by 2 and this is x by 2. So this mass would have been lambda times x, because lambda is mass per unit length and x is the length, gets substituted here. So change in potential energy will be mass into acceleration due to gravity into change in height. Change in height is x by 2 plus x by 2, that is x. So this is the decrement in potential energy, right? And increase in kinetic energy will be half times mass into velocity square. The total rope has gained a velocity of v, so mass of total rope will be lambda times L and velocity is v, so half lambda L v square. This is the increase in kinetic energy. So we'll just equate these two terms, right? So let me erase this here and I'll write. Okay. So, yeah. So for energy conservation, you can write lambda x square g as a half lambda L v square. From here we can write 2x square as L v square upon g. So this is an important relation between x square and v square. So x and v are our two unknowns and we have two equations, so we can easily find out the x and v. As we have asked only about v, I will just substitute x in terms of v. Let's substitute the value of x square here. So we'll get v square L as L square by 2 minus L v square by g into g. So this will come out as v square L, or let's cancel one L from both the sides. So we'll get v square as Lg by 2 minus v square. So v square will be Lg by 4, or v will be root under Lg by 2, and that's the answer for our question. Oh, sorry. Yeah, so this is the answer. If you can do the wrong method that I have mentioned initially, that you just take the whole L by 2 length gets slipped to the right hand side and then only the rope gets detached, you will get some different answer, and that is indeed a wrong answer. So that's a very common mistake everyone does in this question, but you need to be very careful that it's not necessary that when all the rope of the left part gets slipped over, then only the rope gets detached. So that was that's the actual catch of this question. So that's all for today, and I hope you have enjoyed this question, and thank you. We'll bring some more problems, more interesting ones in next videos, so stay tuned.